So very good afternoon to all of you, or rather it's still a morning. So very good morning to all of you. In this class, we are going to learn fundamentals of spatial filtering. Remember the last class we talked about point operations which are at 1 cross 1 pixel level or single pixel level. They were typically called as, if you remember, intensity transformations. So now we are going to extend the domain. We are going to move from a single pixel operation to multiple pixel operation and see how they work or what are their mechanics. Can you all hear me? If you can, then please confirm it. That's right. Thank you, Pankuri. Thanks, Chintan. So, other thing that we are going to learn apart are linear spatial filters. I will be taking only one example maybe today, and then I will take some other examples in the forthcoming lectures. So there are non-linear filters also, but most likely we won't be cover them up in today's lecture. We will take them up in the forthcoming lectures. So what do we mean by filtering? So as you all know, filtering, we are all familiar. You pass your content through a mesh. Mesh takes out a certain things out from the content and passes the remaining. This is typically called as a filtering process. Now same thing we are going to do with an image. We are going to pass the image through a mathematical operation, and that mathematical operation will bring some change in the image, and that process is called as filtering. Typically it is called spatial filtering here, in contrast to frequency domain filters. Frequency domain filters we are going to learn after 2 chapters. So by that time we can keep it at a distance. Typically the most terminology has come from frequency domain filters, like a low pass filter, high pass filter, band pass filter, from the electricity and electronics course. So you will find that those words are resonating with what you have done earlier. So here we are learning filtering in a spatial domain without getting into frequency domain. Is called spatial filtering. And if the operation is linear, then it is called a linear spatial filter. And if the operation is not linear, then it is called a non-linear spatial filter. So since today we are going to focus only on linear filter, and that too just one. So we will take some time to understand that, look at the mechanics. These will follow later, not today. So here is one of the examples of the filters. This is my original image. We have seen this. This is the origin. This is y-axis. This is x-axis. And these grid lines or small rectangles represent individual image pixels. So these are all individual image pixels. Each pixel, as you all know, has three parameters. One is its x coordinate, other one is its y coordinate, and what was the third one? So if you remember, the third one was its value of its gray level or the value of its intensity. For example, if it's an 8-bit image, so it's anywhere between 0 to 255. Is that clear? So now normally the spatial filtering is achieved by using a filter mask. A filter mask can be of any size. Here what is shown is a 3 pixel width and 3 pixel height. So this is a 3 by 3 filter mask. Remember, if it is 1 by 1, then you are actually dealing with a single pixel. And that is what we have discussed in the lectures up till the last lecture, where we were looking at single pixel operations. But now here we have 3 by 3 image or 3 by 3 pixel operation, and this is one example. We will discuss what are the domains in which this can extend. So let's check this example first. So first get into the image plane. Now in the image plane, the selected pixel is the one which is in the middle of the mask. So if this is 3 by 3 mask, then this pixel is in the middle. So that pixel, I would say, has a coordinate x comma y. So the central pixel, we say that right now the mask is mounted on the pixel x comma y. So if the mask shifts, say to one place to the right, then it will be positioned here and its peripheral elements will be positioned here. So remember that part. We'll come to it later. Now the central pixel is addressed as x comma y. Then obviously the image pixel which is next to it, where this element of the mask is mounted, is x y plus 1. Remember, this is y-axis. So it is y-axis incremented by 1. If you are going to the left, then x y minus 1. If you are going at the top, then you are decreasing the x value by 1. Remember, origin is here. So you are decreasing the x value by 1, so x minus 1. And if you are going down, that means you are increasing the x value by 1, so it is x plus 1. If you are at this corner element, then it is obviously x minus 1, y minus 1. If you are in this corner element, then it is x plus 1, y plus 1. If you are in this corner, it is this element, then it is x minus 1, y plus 1. And if you are here, then y decreases and x increases, so x plus 1, y minus 1. So that is how the addressing will happen for the given filter mask. Remember, I am showing you a 3 by 3 filter mask, so addressing is limited up till here. Suppose if I use a 5 by 5 or a 4 by 4, then in that case these numbers will increase. How are the mask elements addressed? So let us look at it. So again, the central pixel is the pivot about which the mask is working. So the central pixel is masked as 0, 0, and to refer to these pixels or the elements of the mask, we are using the term W. So W00 is the central element of the mask. And then in a very same way, we will address the mask. So if you are going here, it's 0, 1. If you are going here, it's 0, minus 1. If you are here, then it's minus 1, minus 1. If you are here, then it's plus 1, plus 1. So on and so forth. So you address the mask elements in the very same way as that of the pixel elements. Okay. Now once this has been understood, then the filtering can be understood little easily. So what the mask does, or sometimes it is also called as filter kernel. So what it does is, it does a sum of products operation between the image and the mask, that is the kernel. So you are all familiar with this operation. You must have heard it in digital circuit design and logic operations. Sum of products, SOP we call it. So you take the products of each mask element with the pixel element where it is mounted, and then sum all of them. That is the normal operation. The elements of the kernel or the mask, whatever kind of elements you choose in the window or in the mask, that decides what kind of operation you are bringing or what kind of nature of the filter is. So coefficients define. So we will look into those things in a while. The terms which we normally use and they are interchangeable are mask, template, and the window or kernel. So these are the words which are often interchangeably used in case of spatial filtering. So get comfortable with them. We are all talking about that window or the mask when you use the terms like kernel, mask, template, or window. So what could be the size of the kernel or size of the mask? The size of the mask or the kernel could be odd, like 3 by 3, 5 by 5, 7 by 7, 11 by 11, and how big it could be. So I had discussed it briefly in the last class and I can talk more, that it could be small like 3 by 3. Remember, 1 by 1 will bring it to individual pixel level. So normally 3 by 3. And how much large can it be? So it can be as large as possible. One can make it. Remember, it also depends on how big is the original image. If your image is, say, 3000 pixels by 4000 pixels, then you can use a large mask as well. However, if your image is a small image, say 500, say 100 pixel by 100, then you cannot use large windows. So the size of the kernels is decided by mostly the kind of operation you want to achieve and the size of the image. Okay, so we discussed so far that it is odd. Why can't it be even, like 2 by 2 or 4 by 4 or 20 by 20? So it can be. The answer is it can be even. However, or it can be mixed even, 3 by 4 or 11 by 20. Just that the odd one simplifies the indexing So you have a very symmetric pattern as we have seen, W0 plus 1, W minus 1. It's very becomes very symmetric. In the odd sized, the center is not on a fraction. So for example, if you are using 3 cross 3 matrix, then you know that the center element has the coordinate 1 cross 1. But if you are using a 4 cross 4 matrix, then the center element coordinate is not an integer. It will be around 1.5 comma 1.5, and then you will have to make some assumptions that it could either be 1 or 2. In that case, it will always be asymmetrically placed, and even the results could be unpredictable in some cases. So the odd sized filters or all odd sized kernels or masks or windows, whatever you call it, are generally preferred over even size or mixed kernels. So do remember that mathematically there is no restriction on the kernel dimensions being odd or even or mixed. Practically there are issues. That's right, Chintan. We discussed that practically finding the middle pixel is decimal. It will get into some decimal. So if it is say 20 by 20, then your indexing is 0 to 19. Then your middle pixel is at 19.5, but there is mathematically, but practically there is no pixel at 19.5. It is either 19 or 20. So in that case you have to keep the center or mount the or define the center either at 19 by 19 or 20, 19 or 20, whichever you choose, but that will bring an asymmetry. I will show you how that asymmetry may affect your final result. So if one is okay with those kind of asymmetries and imperfections, it's fine. But the odd kernels gives they give most of the advantage. Spatially symmetric, center is always integral, some integral value, no point, no need of making any approximation. Indexing is easy. Also, the question is what about 3 by 5? So again we say that when you do 3 by 5, I will show you at the end again that it is slightly asymmetric than a 3 by 3. 3 by 3 is more symmetric. So odd numbered are advantageous, but mathematically there is no restriction. So let's go ahead. As I am reminding you again and again that I'm using the words like mask, template, window, kernel, etc. interchangeably. These are the small window that I defined at the top or earlier. So how do this SOP or sum of product is carried out? So if you look at the this term first, so you could see that the central pixel of the window is mounted on the central pixel beneath that in the image, which we had called as x comma y. Remember, this is the pivot of your window, and although it works on many pixels, we say that right now the window is mounted on x comma y. That is the image pixel which is below or on which the pivot of the window or the central point of the window is operating. So do remember that. This is the central pixel. So you multiply these two values. So you take the value of the window, whatever value you have placed there. Now what value you will put, this will be decided by what effect do you want. So we will come to that. But before that, you put that value there and multiply that with the image value. Similarly, you do for the rest of the terms also. You take the window value of the mask or value of the window or value of the kernel at -1, -1. It is mounted on x minus 1, y minus 1. So you take the pixel value or the brightness value there and multiply that with the value of the window at that point. So you are doing a product here. You are doing w minus 1 0 to x minus 1 y. You are doing a product here. You are doing a product here. You are doing a product. You are doing product for all the terms. Remember how many such terms will appear. So if you observe carefully, it was a 3 by 3 window. So the 3 by 3 window will involve 9 such product calculations. So there will be 9 such product calculation and then all are added together. Now once they are all added together, then it is assigned to a new image pixel at the same location xy, which is here. So what actually is we are doing is we are taking the original image f, taking its each pixel, applying or making a window or a kernel to act on it and creating a new image pixel. So this will be stored as a new image, not replacing the f of xy in the original image. Original image is still there for the available for the calculation. Do remember that. You will be soon doing this operation in your laboratory using Python. So at that time, do remember that after this is carried, you create a new image. This is the, so I hope this brief explanation explains everything. You are doing 9 by 9 product operation. Sorry, you have a 3 by 3 example I am taking. So you are doing 9 product operations and 8 sum operations, adding all the terms together, and then one assignment operation to us make this. So now you will find that it's a huge task as far as computational challenge is concerned. So for example, if you have a 100 by 100 pixel image, let's say, to be very moderate. How moderate? 100 pixel is a 10,000 pixel. 10,000 pixel is a very small image to a current standard. Generally, most of the simple mobile cameras these days have standard 12 megapixel imaging techniques. At least the if you have purchased one in last 2-3 years, they are at least 12 megapixel. 12 megapixel is 10 power 12 into 10 power 6 or 1 into 10 power 7 pixels. 10,000 is, if I'm talking about a 100 pixel by 100 pixel image, then I'm talking about 10,000, 10 power 4, so 1,000 times is smaller than current standard. So I'm talking about a very moderate image, 100 by 100 100 by 100 pixels. So that becomes 10,000 pixels. Remember, I'm doing how many operation for each pixel? So as we have discussed, 9 product operation, 8 sum operation, 9 plus 8 will give you 26, sorry, 27, 9. plus 8. What am I adding? 9 plus 8 is 17. And one assignment operation. That is 18. So total is 18 operation. But if it's a 100 by 100 pixel image, then there will be 18 into, this is for 1 pixel for 18 operation. To create 1 pixel of output image from 1 pixel of input image, you are doing 18 operations. So to create 10,000 pixel of output from the 10,000 pixels of input, you will create, or you will have to do 18 into 10,000 operations. So many operations you have to perform. So it is a computationally challenging. That is why the DIP mostly grew, and it's a very fast growing subject in last 10 to 30 years. So because most of the DIP algorithms and everything have come into practice only after the advent of fast scale computers. Okay, so look at this now. This is the short way to write down the same image. Now, how do we write? So you can now see that it's a product. So you are taking a product of window to the pixel location, pixel function of intensity value of the given pixel. Window is given by st, and this is given by x plus s, y plus t, and it varies from some value minus a to plus a. In this case, it varies from s is equal to minus 1 to plus 1. So when you say minus 1, then the minus 1 comes here. This also varies from minus 1 to plus 1 in this case. So you are going from minus 1, minus 1. This is minus 1, minus 1. So everything will become minus 1. And when this becomes plus 1, then you come over here. And when you carry out this double summation, you actually do this completely. So first you change your t value. I hope everyone knows how to do this. This you will implement in Python by using nested for loop. We call it as nested for loop. The outer for loop will take care of this summation, and the inner for loop will take care of this summation. So first, keeping a value fixed, you will exhaust all the b value, that is minus 1, 1, sorry, minus 1, 0 and 1. So minus 1, 0 and then there will be 1. So once you have exhausted all the b values, then you change a value. In this case, it will change from minus 1 to 0. And again, you exhaust all the b values and then you go for the last one. So I would recommend you to expand this equation and practice it. That will give you an insight of this particular expansion, and if there are more such equations, then I would always recommend that you expand the equations and check. Now most of the time this is carried out by two equations, either two processes. They are either called as correlation or convolution. So what I am writing over here is, or what I had written just above in the previous slide, is the correlation. That operation is called correlation. This we had written. If you revert the window, that is, instead of, you take here the first element of the window, top left, multiplies to the top left pixel element beneath the window. Now if I revert the window, that is if I take the top left element of the window and multiply it to the bottom right element of the pixel. So if it's here, remember I put minus s and minus t. Let me speak it correctly, the frame of reference that we are using. So if you look at here, I am using, let's go to this. Here we have used plus s and plus t. So we take a particular element of the window and we are multiplying to one corner element of the image pixel. Now that this equation is the same, but here you can see that I am putting a minus sign. That means I am switching the corner. So I am taking the particular element of the window and multiplying to the other corner of the other corner pixel. So this is in principle reverts or rotate the window by 180 degree. So I'm going to show it by an example. So if that happens, the process is called as convolution. So remember the two processes we use, correlation and convolution, both are sum of the products and they achieve different purposes. In the shorthand notation, they are represented by a blank star here and by a solid star here. So let me demonstrate correlation and convolution by a simple example. This is correlation. To keep it simple, I am using a one-dimensional matrix. So this is my original image matrix. Let's say F 0 0 0 1 0 0 0 1, and this is my window or kernel. This is my window or kernel 1 2 3 2 8. Now I want to carry out the correlation operation. So I will, this is the, this is 1 cross 3 window, and this is the central, or instead of starting from center, here we can simply start from the 8 just to give you an example. So we will align the window on one side at the first element of the F, that is this one 0. So this is my alignment now where I can start my correlation operation. Now I will see that nothing is there for these element to take product. For this element to multiply, 0 is available. So all I can do is, one of the ways it is handled is you make a 0 padding. So for all other elements, you put a 0 padding. So generally the padding is applied and towards the end it is rejected. You will need the padding at the end also. So once the padding has been put, now you start multiplying. Now remember, this F that I have chosen over here has 1 at this point, while at rest of the points it is 0. Okay, so if you plot a graph, then it is 0 at all other point, but at this point it shoots up and then comes down. So it resembles a peculiar kind of function. What is that function? which is 0 at all points but has a height 1 at one point. So it is called a spike function. It is very much akin to a delta function that you have learned earlier. If I put more riders, it will become a delta function. So we are actually taking a window and applying it to a delta function. So let's see how does this work out. So you multiply 8 to 0, multiply 2 to 0, multiply 3 to 0, multiply 2 0 and 1 0. And after you have multiplied, now since they are all 0, answer is 0. You add all of them. Once you have added, again 0, then you assign. Whom are you going to assign? So remember your starting point is this. You assign all the addition to this one. You have assigned all the addition to this one. But remember that would remain at 0. After that has been done, the window will shift by one position or by one pixel. So earlier 8 was positioned here, now 8 is positioned here. Once the 8 is positioned over here, you repeat the same process and again the answer is 0, assign that to this value and this will continue. I recommend you people to check the other steps also. Okay, now what happens when you, so wait, what was I talking? So your correlation results are written separately, remember, in G, not in F. So we are writing the correlation results over here. So what will happen when 8 will reach to 1 here? So when 8 will reach to 1, in that case, when you multiply 8 ones are 8 will survive. All the rest would still be 0. So you get the first term as 8 over here. So you get 0 for this, 0 for this, 0 for this, but you will get 8 for here. Okay. Then further case, when 8 goes at a step after 1 and 2 is aligned with 1. So when 2 is aligned with 1, 2 into 1 will give you 2 surviving and the rest will vanish. So the 2 will survive, the rest will vanish. Similarly, when 3 will align with 1, then 3 will survive. When 2 and 1 will align with 1, they will also survive. But at rest of the places, the SOP will remain 0. The process will end when 8 reaches at the last pixel. So when the 8 reaches at the last pixel, the process will end. Then after that you remove the padding or whatever extra padding has come. You remove all those things and you retain only those terms which were necessary. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And this is your correlated results. So you can see that you have taken your original image matrix, you correlated with a window and you got a different result. In this case, particularly this case, since you are having a delta function over here, the job of the delta function was, or correlation of delta function was to recreate the window at its location. So the window has been recreated. But what we have seen interestingly, that here what was all dark and one bright pixel, now it's no longer the case. You get a dark, then a bright, and then some varying intensity, and finally the intensity drop. So your entire image gets transformed. Going ahead, what happens in convolution? So remember the convolution when we spoke about, we did say that in convolution the definition is given. Remember those plus signs had become minus, and the impact was that the W was rotated by 180 degree. So if you look at this one, this is 1 2 3 2 8. Here we rotate it by 8 2 3 1, 8 2 3 2 1. So window is rotated now, and again if you do the same operation, then it is called convolution. So the operation remains the same. The flipping of the given window makes it convolution. So again, since the operation is same, the result is similar here. 1 2 3 2 8. Compare this with here. So what is happening is, look at it. If your window is 1 2 3 2 8, the correlation produces the window but in an inverted manner. That is 8 2 3 2 1. And that is how you will see why convolution is important. So if you are okay with the inverted window creation, if you are okay with inverted window creation here, then it's great. But if you are not okay with inverted window creation here, if you want a similar window 1 2 3 2 8, then what you will need is a convolution. You have to flip it and then do it, and that is where the convolution is needed. So depending on what kind of results you want, you can choose the kind of operation. Now this is in one dimension. Let us quickly look at some examples in two dimensions. This is my two-dimensional image, again a delta function. Rest of the places at 0 except at the center. This is my window 1 2 3 4 5 6 7 8 9. Again it's a 3 by 3 window. So remember, now I will start correlating and convoluting it from this end. So I need some padding. So some padding is generally created. So this is 1 2. Remember, a 2 element 2 rows padding here is created, and here it is 2 column padding which is created. So now I can mount my kernel in or window at the corner, so that this 9, go back, let's go back. So this 9 is first mounted at this point. So remember, this 9 is pointed or mounted here. So these two rows and these two columns have nothing to correlate, and for that we did the padding. Once the padding is done, then the 9 is at this corner and these two are zeros. Now the correlation will happen in two dimensions. So you multiply the window element 1 to the image element. You can visualize 0 beneath 1, then multiply the two. Visualize this image in two planes. Upper plane is window, lower plane is image. You multiply element to element from the first plane to second plane. So 1 to 0, 2 to 0, 3 to 0, everything 0. Assign that value to this pixel and it will become 0. So it will remain as 0, which is here. And then after that, this entire block will shift by 1 position to the right. So it will start from here. 1 will come here, 4 will come here, 7 will come here, 2 will go here, 5 will go here, 8 will go here, 3 will go here, 6 will go here, 9 will go here. So the entire block will shift to the right by 1 position, repeats the same operation, again shifts by 1 position, repeats the same operation, so on and so forth. Remember, the moment 9 reaches at 1, that is when it mounts over here, it will go to the end, right end, come back, 1 down, come back, then go to the right, then 1 down, come back, so on and so forth. So when it is mounted here for the first time, the 9 into 1 will give you 9, that will survive, the rest will be 0, so this element will become 9. Similarly, when it is mounted like this way, then which element will coincide with 1? Can you tell me? If you mount it this way, so if you think carefully, you will find that 8 will coincide with 1. So the 8 will survive, rest will become 0. So it is now creating the different elements, and these elements will be created. You can see that after the correlation, the window has been recreated at the center, and what is happening is the window is flipped. So 1 has come over here and 9 has come over here. So it's a 3 has gone here and 7 has gone here. So it's a 180-degree flip. In coming from here to here, I have removed those padded elements. So padding has gone. So this is how the correlation has happened. Now, if you don't want this flipping, then you have to carry out the convolution. How does the convolution happen? So you first flip the window, rotate the window itself. 9 instead of keeping here, you take here. 3 you keep here, 7 you keep here. And then you do the process. You get your proper window back. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is the convolution result. So remember, the convolution is commutative, it is associative, and it is distributive as well. Correlation is indeed distributive, but associative and commutative properties don't hold for correlation. You can explore more on that. Now, I will just give some brief examples of the filtering and take one example before we end this discussion. So, as we said, we are discussing linear filters. The typical word which is used for linear filters is, say, a low pass filter. So typically in electronics course, and even here later when you do frequency domain filtering, you will say that a low pass filter allows lower frequencies to pass through while attenuates the higher frequency components. We will see in detail later, but for the time being, the higher frequencies means the edges and the sharp details in an image. If an image has lot of edges, lot of small elements, छोटे छोटे parts हैं. For example, leaves of a tree. If you take an image of a tree, then small details means the sharp details means the image of the individual leaves. There will be thousands of leaves. If you take an image, then that is the sharp detail. These are called high frequency component. If you use a low pass filter, then it will attenuate the high frequencies. That means it will suppress these details. What about the low frequencies? So, of course, suppressing these details means leads to an image blurring. Image will get blurred. A high pass filter is attenuating low frequency component. What is a low frequency component? So any large object in the image. So for example, if you take the image of a tree, then the overall appearance of the tree, shape of the tree, overall whatever shape it has, or if there are multiple 3 4 trees, then those overall shapes are the large shapes, and they are going to be low frequency components. So the low frequency components are slowly varying characteristics. If they are suppressed, then generally the image looks very sharpened. It has very sharp, the other edges becomes sharper. So these are the two terms which are often used: low pass filter and high pass filter. But remember, don't get confused from the word frequency right now. We are not using any frequency dependent filtering as of now. We are using these terms because they are commonly used, and results are also similar, but we are doing spatial filtering. A third kind of filter that normally comes into talking is a band pass filter. Typically it is used to remove different kind of noise. We will check that when it will come. So let's take an example of a spatial filtering. This is low pass filter. Remember, what does the low pass filter do? If you recall the discussion we had just, it will remove the high frequency component. So in case of the image of the tree and leaves, the component of the individual leaves will get suppressed. They will look blurred. However, the large scale structure of the tree would be retained or restored. Then such an image or such a filter is typically called as a low pass filter. The other word for such a filter is smoothing or averaging filter. We will see why do we call them smoothing and averaging filter. Smoothing because, as I said, the details are suppressed, image looks more smoother. The other example is if you apply this kind of filter to a face, image of a face, then it will suppress the small blemishes, patches, marks, pimple marks, etc. from the face successfully. That is a high frequency component. But low frequency component like the the size of the face, the nose, ears, eyes, lips, etc. would be retained. So if you have seen, some of the mobile cameras have what we call as the beauty mode kind of thing in their camera app. So they use these kind of filters. How do they work? So a typical kernel, one of the example I'm right now focused on this is this one. So what it does is it has all the element as 111, 111, 111. It's a 3 by 3. It can be even more. So if you take each element as 1, then what you are doing, think about it. You multiply this to the pixel value beneath it. Imagine this is mounted on an image. So you multiply 1 to the pixel value. But remember, multiplying by 1 does not change the pixel value. So you take that means you are picking up the pixel value, adding them all. So all the pixel values are added. and then they are divided by 9, the total number of pixels. Typically what you are doing, so if you think about it, you are doing an average. You take all 9 pixels over here, pick up their values by multiplying by 1 by doing this SOP operation, sum of product. Product is by 1, so there is no change in the value, and you sum all of it. Add all of them together. Whatever value you get, you divide it by 9. So you get an average. So this is average without a weight. You are not applying any weight. All elements are chosen uniformly divided by total number of elements. And that gives you the averaging. So the central pixel in the resultant image will have an intensity value which is the average of the surrounding 9 pixels. So if you have a 3 by 3 kernel, then the resultant pixel will be an average of 9 pixel value. Similarly, if you have larger box here, that is why it is called box kernel. Suppose if you have 5 by 5 or 7 by 7, then in that case the averaging will increase. This is a weighted average. So here you give different weightage. Central one is given little more weightage. So you are taking the impact of the neighboring. These one are given second best weightage by multiplying by 2. The corners are not given that weightage. So that means you are, if your image has vertical lines and horizontal lines as to begin with, and you know that you don't want to destroy them, then you give more weightage along this axis and this axis, but you don't give weightage across these two sides. So even though the averaging will happen, your resultant image will still have stronger representation of horizontal and vertical lines. So let's check the results of any such operation. This is my original image. This is I think has to be around 100 pixel by 100 pixel, and what I am using is a 3 by 3 kernel over here. So if I use a 3 by 3 kernel, it will bring some sort of softness to this. How? You can see these edges, these are slightly blurred out over here. Now I'm bringing a 5 cross 5 kernel, so the geometric area or geographical area is more, from which each pixel over here is drawing its value. So you will find that these smaller details are vanishing. So these points are very much separable. They become indistinguishable. But larger details are still retained. You know that this is a dark patch, this is A and this is A. You can still read this. But what will happen if I go to 9 by 9? And you will find that the reading, the first one is more challenging. This is original. All these are gone. You cannot distinguish them at all. Here you can say that there is some point. So you can see this, it starts averaging out or blurring out the smaller detail. That is why we call it as a a low pass filter. A low pass filter suppresses the those components of the image, those are small in size and vary quickly. That is high frequency component. This is 15 by 15 image, and you can see that a lot of things has blurred out. If you are watching it on a mobile screen, you may find it difficult to see the difference. So since the recordings are available, I would I recommend that you also see it on your laptop or TV screen so that these differences become very clear. So here you can see that all are gone. First three, four letters here you can't make out what it is. Last one you can still. This is still there. Remember, this is the largest of the structure and it is still there. This box is still there. But what happens if I increase it further? So if I make it 35 by 35, then you will find, remember this is whole is 100 by 100, of which this is 35 by 35. 35 by 35 means the size of the window is one third of the image. It should be like one third is here and one third here. So the window is this much big. And when it is being run, you can see that it creates a huge averaging effect. So I go back and see once again. This is a 3 by 3, hardly any effect. 5 by 5, small details start to vanish. Then I increase it to 9 by 9. These smaller ones have gone totally. Some small letters are also gone. 15 by 15, they are of course vanished. They are also not visible. These letters are now not distinguishable. And at 35 by 35 you can see that now 35 by 35 is a huge pixel for this kind of image. So depending on what kind of, that's what DIP is, depending on what kind of image you have, what kind of averaging you want, you can always select by trial and error method the size of a filter by which you can apply averaging. You can use the filter which is, this was all applied was plain 1111 filter, not weighted. You can even apply the weighted filter and see that the results are slightly different. So maybe we can stop here today. We'll continue in the next class with some other linear filters and then non-linear filters. Thank you.